So next class I will request like I promised a COMSOL engineer who is also teaching assistant for this course to show you how can you use a COMSOL multiphysics tool which is for simulating the sensors. You know, when you are fabricating a sensor on an actuator, you have to go for a clean room environment, one thing. Second thing, you have to use silicon wafers, right. You have to use several technology available within the class 1000, class 10,000 clean room environment, right. Now when you fabricate the sensor, after fabrication you do not have to you will test the sensor, right, but it may not be giving you the values or the properties of the sensor would not be as per your understanding, and that is why before you fabricate the sensor you need to go for simulation. So that you understand that using this particular parameter, suppose a sensing layer, what is the thickness, heater, how should you fabricate the heater, what should be the width, what should be the spacing between the lines of the heater, right, what should be the thickness of the insulating material in between, how the temperature how the heater temperature would affect the sensing material. If you apply a force on a piezoresistive sensor, how much it will bend and how much is the change in resistance. This everything you can first work on simulation simulation tool, and once you get the data from the simulation tool you can go for the fabrication, right. So before fabrication the simulation becomes an extremely important component when you talk about MEMS based sensors and actuators, or in other terms any sensors and actuators, right. So the lecture that will be taken by Uttam would be on understanding how can you use glucose sensors, particularly interactions with glucose sensor. That will be first lecture using the COMSOL multiphysics tool, and then we will be talking about other lectures in subsequent classes. The other idea is to also make you understand how can you use the thermal actuators and resonators. Also I want to show it to you how can you use the heater as a simple example for the so heater is some simple example of using COMSOL multiphysics as a simulation software, right. So let us see how can you use say glucose sensor with COMSOL multiphysics, and I'll be talking about more about this particular sensor at a later stage of the lecture. Till then you take care, have fun, bye.
So welcome to the course of sensors and actuators. Today we are going to talk about how MEMS simulation could be used for performing simulation. So this is the agenda of what we are going to talk today. We will first try to understand why we are going to talk, why we need simulation. Second is we will talk about what are the different kinds of simulation that we have in COMSOL multiphysics. There are different kinds of devices that can be modeled. Some of them, as you can see on the slide, you can see that we can model piezoelectric devices, we can model piezoresistive devices, we can model actuators, we can model which are having the exertion based on stresses or on thermal. Then we have fluid structure interaction that could be modeled to make some kind of actuators or pumps, and then finally we have chemical sensors. So all these different kinds of sensors and actuator devices can be modeled in COMSOL. But the first question that comes into the mind of a person who is asking if they need simulation is why simulation. There could be different reasons to move into a region where you want to do simulation. One of the reason is that you want to compare your experimental data with the simulation data. Why do you want to compare that? Because the comparison will help you to understand the underlying physics. Because once you know what is the physics is, you can actually change the scope of working of your device and get to new different kind of results. So that is one of the reason, that is to compare your experimental data with the simulation data and try to understand their physics. The second is to predict. To predict means you have your operating scope. For example, you have a thermal actuator, and by giving a voltage of 1 volt to 5 volt, you are getting an actuation of 10 micrometers to 100 micrometers. But you don't know that if you give 100 millivolt, or if you give around 10 volts, how much the actuation would be. In addition to it, you also don't know what would be the stresses developed within the device, and if it actually breaks or not. So such kind of prediction, where you are working out of the scope of your input source, those kind of prediction you can perform with a simulation tool. And then finally, you can create a methodology. What do we mean by it is that you can make your own mathematical model. In the end of the day, whatever simulation you are doing, whatever experiments you are performing, the main aim or the objective is to come up with a mathematical models. So in COMSOL you can make your own mathematical models. So these are the different common types of MEMS materials that are available in the market. We have ferroelectric materials, we have ferromagnetic materials, and then we have ferroelastic materials. Over here, the property of all the three material properties are changed based upon the three different material property. The first is the electric dipole moment, the second is the magnetic dipole moment, and the third is the stresses being developed within the material. So based upon that, you get different response. So if you see this slide, which talks about on the left side we have input energy, and on the right side we have output energy. So if your input is mechanical force, or it could be converting into stresses, and you take the output as magnetic energy, that effect is known as magnetostriction. Similar to that, if your input is mechanical, your output is electrical in order of like current, it is known as piezoelectric or piezoresistive device. Then similarly, if your input is magnetic and your output is mechanical, you have magnetostrictive, and if the output is thermal, you get magnetocaloric effect, and if your output is electrical, you get magnetoresistance. Then if your input is thermal, you might have heard about shape memory effect. So this is an example of this is a classic example of stent, that is a biomedical device that we use or we introduce within the blood vessels. If you read about it, you will know that the stent that they introduce within the blood vessels of the heart is, first they actually push it from radially outwards towards the central axis, such that the radius of the stent reduces, and once they introduce within the blood vessel, it can actually come to its original position of the larger radius. So this kind of simulation can be performed in COMSOL. Then we have pyroelectric effect, and then finally, if your input is electrical and you want to get mechanical output, then you use piezoelectric, and then we have thermoelectric effect if you want to create the output as thermal. So this is the different kinds of physics that could be solved in COMSOL. We have electromagnetics, we have structural, we have acoustics, then we have fluid dynamics, then we have heat transfer, and then finally we have chemical. So all these are individual physics, but no one is stopping you to couple two or more physics together. So for example, you can couple electromagnetics and structural, electromagnetics and heat transfer. And there is no limitation on the number of physics coupling that you can have. You can also write your own equations using the equation interface. You can optimize your design, so you can do shape optimization, you can do topology optimization, you can solve for inverse problems over here, and then you can also interface with other softwares such as MATLAB, Excel, or SolidWorks. All of them can be actually interfaced with COMSOL. So all of this thing what we do is in model builder, and one of my colleague in the demo will show that how to actually make the complete model, and from that model you can also create a very simplified app. This app is like a very simple interface which will help you to come up with a very simple user interface which will help you to change the parameters and see the results. So let us go with the MEMS modeling, and we will talk about different devices that could be modeled in COMSOL. The first one is the piezoelectric property. With piezoelectric property, we can have two types of devices. One is the actuator, where your input is voltage and your output is displacement. That is, you give some kind of 1 or 2 volts and you see if you get a movement of your device or deformation of your device in order of micrometers or mm. Another type of devices that you can make with piezoelectric material is sensor. That is the opposite of what you see from the actuator. That is, your input is force, that is, it will create a stress within your material, and the output is going to be voltage. This voltage could be in order of millivolts or microvolts or in order of like few volts. One of the example of piezoelectric device that you will see is a piezoelectric energy harvester. This all the examples that I am going to talk about is, as you can see in the bottom, is available in the link in the bottom. If you just click on the link, you will be directed to a web page, and once the page opens, as you can see over here, so this is an application library model. So all the models that we are going to talk today are a part of the application library online, as well as once we install COMSOL. And over here, if you download the application files, you click on that, you have an option of PDF. So once you open the PDF, you will see that it has a complete documentation, that is the complete theory part. Then it has the explanation schematic. In the case of piezoelectric energy harvester, that will come in a minute. It talks about the results and the reference with which we compare the results with, and then the step by step process to make the whole model. Okay. So all the models that we are going to talk about today are already available in the internet. If you want to download the model, you can even download that particular model. Okay. For that, you need to actually make your own login account. Okay. You can also search in the internet. For example, you can search for piezoelectric energy harvester COMSOL, and you will be directed to that particular model. You can see the first link that opens is the piezoelectric energy harvester, and you can download the application file, the model file, and you can start working on that particular project. The good part of these models which are already available is that you don't need to work from scratch. You can take this model, change the geometry, and you can get the results. Okay. So this example of piezoelectric energy harvester, so as you can see on the screen, it has a bimorph. So it's 2 layers that are made up of piezoelectric material, and the main application of piezoelectric energy harvester is, for example, in the shoes. So people are making the shoes where they can convert the vibration energy that comes when you walk into the electrical energy and store it into the battery. The same battery can be used for powering your watches or your mobile phones, for example, right. One more example is the motor or generator, which is continuously vibrating. So those vibrational energy goes for waste. So what if these kind of devices we can actually put onto such kind of vibrating sources or motors, such as motors and generators, and that could be converted into electrical energy. So you can see over here we have the 2 layers of piezoelectric material, and this is the proof mass which is actually vibrating, and this is the supporting structure. You can see based upon the different loads how much, what is the resonant frequency, and the mechanical and the electrical output energy that the device is giving. So over here the input is mechanical energy and the output is the electrical voltage. Then we have surface acoustic wave gas sensor. So over here what you see over here is 2 interdigitated electrodes, IDE, and on top of the IDE that you can see over here and here is the film of PIB, that is polyisobutyl, which is deposited on the IDE, and on the bottom we have the silicon wafer. and based upon the gas. So, if you open this documentation, so let me just open the model file or the documentation. So, I will just saw gas sensor COMSOL. Just need to search over here like this, and you can open that particular model. So, you can see this is the actual structure that has been modeled. So, this is the actual structure in 3D. However, in COMSOL we try to understand if there could be a simplification of your complete geometry, because in simulation tool we actually mesh the geometry, and it requires somewhat of time if you go for directly a 3D geometry. So, what we do over here is we make a 2D cross section. So, you can see this is a small white surface that is what is modeled in COMSOL. So, once you open the model you will get to know, and this is the first ID and this is second ID, and then finally we apply periodic boundary condition on left and right. Okay, and based upon the gas which I think is, yeah, so we have I think it's DCM. So, DCM actually stands for dichlorine methyl, I guess. Yeah, so we wanted to understand how much is the gas getting adsorbed on this PIB film, and if it is getting absorbed, how the density of the PIB film is changing, and based upon the density the resonant peak of your device is actually changing. So, this kind of simulation is performed. So, you can see this is the gas dichloromethane, which is modeled over here. Then we have bulk acoustic wave composite resonator model. As you can see over here, again this is a 3D structure, but what we model is a cross section of it, that is a 2D cross section, and we also have a 3D example for this BAW sensor, that is bulk acoustic wave. Over here also we get a frequency response, resonant peak, anti-resonant peak, and from that we can understand about the BAW resonator. Then we have piezoelectric shear actuator beam. In this case you can see that there are this is a composite material. What you have there is two different layers, top and the bottom, and in the center that you see over here is the piezoelectric material, and it is having a foam on the left and the right hand side. Over here what we give is an input as a voltage to this piezoelectric material, and what you see is the output is the structural deformation of your cantilever beam, which is fixed on this boundary, and it's freely moving on the all the other remaining boundaries. So, you can see that because of the polling direction, which is I think it's in x direction, that is over here on the right side, you will see that the bending is on the top side. So, if you reverse the polarization of the on the piezoelectric material, you will see the bend towards the bottom side. So, it is actually working as a electrical actuator, right. So, this model is also available in the link that you can see in the bottom. Then the next type of devices is piezo-resistive device, which means the change in resistance once you apply a particular force. So, this is a linear model that we have seen over here, but you can make more complex nonlinear devices from this kind of devices. Yeah, one of the example of the piezo-resistive pressure sensor is a diaphragm that you can see over here. So, let me just open this documentation. So, I just search for piezo-resistive. So, I can just search from here, or you can just go to comsol.com, and over here you can just go to model and application files, and over here you can just search for piezo-resistive. Yeah, so you can see that this example of piezo-resistive, and over here you can just download this model file, and you will get to know the physics that we are solving for. So, what we have over here is a diaphragm that you can see on the left side, and this part is zoomed on the right side. So we have the N doped and P doped silicon material which works as a piezo resistor, and we apply a particular voltage across it to see what is the change in the resistance, that is the output current, if we apply a force on this particular diaphragm. So you can see the force that is applied over here. So this is the force that is applied, and this is the stress that is developed on this film. So you can see how the stress is changing based upon the force that we are applying, and what the current is it changing. Then we have electromechanical and thermal actuators. One of the example is capacitive pressure sensor. The capacitive pressure sensor is like very well known sensor which is mainly used in mobile phones as a touch screen touch screen devices. Then we have biased resonator. This is nothing but electrostatically actuated cantilever beam, and then we have one more cantilever beam which requires the thermal energy to make it actuate, because that's why it's known as thermal actuator. So let's just talk about capacitive pressure sensor example over here. So I just go to COMSOL again, and I just search for capacitive so you can see this example has opened over here, and if you just download the model file documentation, so this is the 3D structure that we have modeled in COMSOL. However, to reduce the complexity of your model, what we have done, we have only modeled the quarter of the complete structure. So you can see this is the quarter structure that we have modeled, and we have applied symmetrical boundary condition on left and on the right side. Okay, and then we apply the pressure on the top side. So over here from top to bottom we apply the pressure which actually gets distributed, and there is a capacitor formed. So you can see over here, if you see the next figure, so you can see if this is, it is a zoomed part of this cross section in the center. So this is the air gap, and we have conductor on the top and the bottom, and based upon the deformation that we give, that we apply the force with, it changes the distance between these two conductors, and based upon that the capacitance actually, which is inversely proportional to the distance between the two plates, changes, right. So you can see over here, as you go on applying the pressure, the capacitance is non-linearly increasing. Okay. So this is how you can model the capacitive pressure sensor models. Then we have biased resonators. So this is also available in COMSOL, you can understand that. So there are two different types of example. One is stationary analysis, then we have pull-in voltage. So the amount of voltage that is required to these two bend the cantilever beam to bend a certain amount is a pull-in voltage. Then we have a different example of surface micro machine accelerator. This is an example which talks about if you want to know the velocity of or the acceleration of your particular device. In such kind of application, this accelerometer is used. We have, for example, right now currently this accelerometer are used even in mobile phones and in aircrafts to understand at what accelerations are you moving on, and if you want to play a particular game, this kind of accelerometers are used. So this is also a model in COMSOL Multiphysics. You can see this link over here. And then we have thermal actuators. So I will just open this example over here. So I just go to my application library, and then I will go to thermal actuator. I will just search for thermal actuator, and you can see we get an example of thermal actuator, Joule heating for a thermal actuator. So this is the actual thermal actuator that we are going to model. We have the model way for. These are the two anchors that you can see over here. That these are three anchors which are fixing the device. So this part is actually fixed to the particular substrate. However, this all the other part are susceptible for motion. So this part can actually move. So you can see there are two types of arm. One is thin arm, and these first two are thin arms, and the third one is a very large arm. So as you can know, if you allow the current to pass through smaller area, at those areas will be getting heated up, right. So the top two arms will be getting heated up more as compared to the bottom arm. So it will once it is getting heated up, this will actually get thermally expanded, the top two layers, the top two arms, and because of that this particular device will actually move move towards the bottom side, right. So because of thermal expansion, you will see a particular actuation, that is a movement towards the downward side. Okay. So you need to give the material data like electrical, you have the mechanical and the thermal material properties of your device, and you get the results out of it. So this is the results that you can see over here. You have the plot for the x coordinate versus the temperature data. So along the x axis, what is the change in the temperature. Yeah, this is one more example of thermal micro actuator. So then there is an example of fluid structure interaction, that is you have different kinds of pump. The one object that you can see over here is the micro pump, and this is a very specific type of a pump which allows you to pass through the flow only in one direction. So you can see the direction over here, it's from left to the top tank. So there is a sump over here in the top which allows to save the water for some time, and then it will after the second period. So this is the first the image is for the first cycle, and on the next cycle the amount of water that is or the amount of any liquid that is saved within the sump is then given through over here to the right side, right. So this is a kind of a micro pump, and you can see that there are structures which are actually getting bended, right. So these are the elastic structures that are getting bended, and we solve this using the fluid structure interaction interfaces. Over here also you can see this is a structure which is used to obstruct the flow of the fluid over here, and that is why you can see there is more pressure, and we actually require moving mesh ALE technique to actually model this kind of deformation, because we start off with a particular mesh. However, as the time goes by, this structure bends, so the mesh also needs to be changed accordingly. So these are the two examples that has been modeled. One example is fluid structure interaction. So you can just search over here, fluid structure interaction. So there are many examples of fluid structure interaction. We will talk about micro pump and this FSI. Yeah. So you can also see the animation of the fluid structure interaction that is over here. So you can see that when the flow has started, it starts to bend, and because of that there is a kind of a vortex that is developed below the or after the structure. Okay. So these lines have been plotted with streamline plot, and what you see is the pressure that it is developing over here. And this is the example of a very highly elastic material and how it is actually wiggling. based upon the forces that is applied to this particular structure. Then we have an example of micro pump. So let me just open the example model over here. So this is the initial position of the this particular device that you can see over here. This first device and second device, and both are elastic material. So they can actually bend based upon the forces that is applied on their surface. And what we give is an oscillating input that is through the pumping mechanism, and we allow the current to flow. We allow the flow to happen only in one particular direction, right. So you can go through this documentation, and this is the mesh you can see over here. This is the mesh that is modeled over here, and this is how you can see that the flow is happening toward the right side, and over here also the flow is actually getting accumulated within the structure. So it's not moving to the right side. Okay, and with the time you can also evaluate how much is the net pump the volume with respect to the time, that is. Then we have the interaction of piezoelectric transducers such as speakers or acoustic sensors such as microphone. So this kind of thing could also be modeled. In this kind of cases, we have the input as for example speakers, as you can see on the right top side. We have the input as the voltage, and the output is in terms of acoustic radiations. So you can also model such kind of applications in COMSOL, or you have microphone where your input is the acoustic vibration and your output is the electrical signals, right. So if you want to search for such kind of examples, you can just go to the application library over here, and over here just search for piezoacoustic material. So we will see some of the example of piezo. So this is an example of piezoacoustic transducer, which converts the acoustical energy into electrical signals. And this is a Tonpil's transducer, which is used in the oceans to understand or to predict the any particular kind of storm that is arriving through the ocean. So this actually helps you to understand vibrations within the oceans. Then we have nonlinear magnetostrictive material. This is a very classic example of the humming noise that we hear when we are near to the transformer. So in that case, because of very high magnetic field, the ferrite material or the magnetic material, they actually expand and also contract based upon the frequency of operation, and that's why we hear a particular kinds of humming noise that comes through the transformer. Those humming noise can also be modeled in COMSOL using the magnetostrictive material models that are available, and you can try to understand if you give different coil currents, how much the magnetostrictive material based upon the some material parameters is changing, right. So you can model such kind of applications also. Then we have chemical sensors such as glucose sensor over here. So this is a strip that you would have seen if you have seen the device where you have to prick your finger and some blood will come out of it, and then you apply to it to a strip, and that strip will accumulate the blood to a longer distance, and it will change its color, and it will if you apply this to electronic devices, it will help you with the help of electro analysis. It will help you to understand how much concentration of glucose is within that particular ml of blood. So this is also modeled in COMSOL. So this requires the chemical expertise. So you need to understand what is the chemical reactions that is happening, which kind of oxidation is happening through this strip, and all those things. So you can see this Michaelis Mentis kinetics is actually being solved within the model. So if you want to access to that model, just search over here as glucose sensor, and you will see that particular example model over here, as well as the link that we have given over here. So if you just open the interface over here, and you can see this PDF, that is the model PDF, and you can see this is the structure that we have made, and the concentration of the blood is applied over here. You can also see the results, how the concentration of ferrocyanide in this case is changing for different kinds of glucose concentration. Okay, and this is also step by step process to make the complete model. Okay, so what we I would like to conclude with is, if you go to COMSOL, so if you just search for COMSOL over here, if you want, this is the first time that you are seeing COMSOL and you want to start learning about COMSOL multiphysics, what I will suggest you is you can just go to the bottom, and there is something new that we have introduced, that is known as COMSOL Learning Center. Okay, so let me just search for it. Yeah, so it's over here, right. So this is a very nice portal which can help you to get started with COMSOL. If you want the trial license, you can reach out to the office, that is, you can go to the contact and you can ask for the trial license. And if you want to also learn COMSOL, you can just go to this learning center, and it has a very nice video platform which will help you to get knowledge about many things. So you can see this is the introduction series, then we have the physics, that is how to add different physics or multiphysics. Then this section talks about the interface, user interface of COMSOL, then the basics of mesh, and then we also have geometry, how to create 2D geometry, 3D geometry, how to create partitions, and then the study. So there are different kinds of studies. So how can you apply different kinds of studies like frequency domain study or time dependent study or stationary analysis. And then finally you have definitions. So how can you give different definitions in COMSOL, and then finally how you can do the post processing of your results. So once you get the data, you also need to post process the result to get meaningful quantitative data from your analysis, right. So this is how you can post process the results, and then how to access material. So you can input the material. So there are many different kinds of materials that you can give, which are also available in COMSOL. But if you want to add your own material properties that is not available in the library, you can add those material properties also, that you can learn from this. How can create your new materials, how to sweep the materials, that is different materials you can use on the same device and see how much is it changing. Then finally we have the application builder, that is, it talks about how to create very simple apps from your complete models, right. So once you open any of this section over here, you will be directed to a video that will be around 15 to 20 or half an hour video, which will help you to get accustomed to that particular section. And this is the example, or all these videos are like at your own pace. So you can pause the video and then try to go to a previous video at any time, and you can learn with your own pace. Okay. So I hope this introduction session would be helpful for you. If you have any questions, please do not hesitate to write us. We will definitely try to look and answer to all the questions. The next session would be also talking about the demo on this particular COMSOL multiphysics. It talks about the GUI, that is the model builder, how to make. So there is a step by step process to make the complete model. So the first step is to make your own geometry. It could be a circle or a sphere, or it could be a cube or anything like that. The next thing is to apply a material property on that particular geometry. The third is to apply physics domain and boundary conditions on that particular geometry that you have made. And as COMSOL is a FEM tool, that is finite element method tool, you have to break your complete geometry into small mesh elements. So we solve at the node points of such mesh elements and we get the results, right. So that is the need that we need to do. We need to mesh the complete geometry, and then finally we apply a particular type of study, that is a stationary study, that is for time t equal to infinity, what is the working of your device. It is also known as steady state analysis. Then we have frequency domain studies, which talks about if you give a harmonic input, that is a frequency of a particular hertz, you give it as an input, how your system is going to respond. And then finally we have transient simulation, that is a time dependent simulation, where you can actually know the transient effects, which are more or less, if you want to do a non-linear study, people go for transient simulation, and then afterwards it's getting stabilized. So those kind of things you can also model. Then we have eigenmode analysis, where which helps you to model or get to the resonant frequencies, or mode analysis to understand which mode of which mode are or could be existing in your device. So such kind of applications could be modeled. And then finally in the bottom is the result node, where you can post process the results. So this would be discussed in detail on how to make the complete model step by step. Yeah, I hope this session was will help you get started to use COMSOL. Thank you.